Hello and welcome to the online lecture for General Physics 2 dealing with the topics of electrical current and electrical resistance. Because in this particular lecture we're going to be focusing on developing a conceptual understanding of those topics and connecting them to the topic of electric potential difference, which we introduced and defined within our electrostatics unit, there are a fair number of multiple choice concept questions embedded within this particular lecture. So I would encourage you, as always, when the question is framed, to consider pausing the lecture, seeing if you can figure out the answer on your own, and then restarting the lecture to hear what my answer is to that particular question. In fact, we'll just start out with one of these questions. We looked at capacitors at the end of our electrostatics unit, and imagine this is a picture where we're looking side-on to a capacitor, which is again two conducting plates, so we're just looking at the edges of those plates. What mechanism could charge the plates and get them to develop a situation where one of those plates is negatively charged and one of the plates is positively charged? We have negative charge transfer from the left plate to the right plate, positive charge transfer from the right plate to the left plate. Both of those actions could result in the charged plates being the way they are, or neither one. It must be some other mechanism. My particular answer to this question is number one. Again, when we talk about negative charges, we're thinking about electrons, and when I think about positive charge, I actually think about protons, which are in the nucleus, and the number of protons determines the identity of the element that you're working with. So everything that I work with, and when I'm trying to understand and explain what's happening in an electrical circuit, is going to involve the movement of electrons. But if you answered number 3, I don't really have a problem with that, because everything that we do can be thought of with a model in which both positive and negative charges move. And in fact, those positive charges need not be protons. In fact, some people, particular scientists that are studying semiconductors, will often talk about electron holes as the absence of an electron. And so if you think about the electron hole or the lack of an electron moving, that could be thought of as a positive charge. It's not going to be that crucial for our discussion whether you think about positive or negative charge moving, but I will default to having only the negative charges moving when I describe circuit behavior. So to connect back to what we did at the end of the electrostatics unit, recall that we said when the plates have no net charge on them, the potential difference, which we symbolize by delta V, between the two plates is 0. But as I transfer charge from one plate to another, I increase the electrical potential energy of that system, and in doing so I also create and then grow an electric potential difference between the two plates. Again, electrical potential difference, delta V, is defined as the difference in electric potential energy per unit charge. So let's consider, still thinking about this system, if I have a potential difference between a positively charged plate and a negatively charged plate, but now instead of keeping them separated and insulated, I put a conducting material, say a conducting aluminum or copper rod that connects one plate to the other plate. What's going to happen? Will negative charge move from right to left? Positive charge move from left to right? Both of those actions, or will we have no charge move? My answer to this, again, is number 1, though if you answered number 3, I have no problem with that as long as you're being consistent in your description of what's going on. Recall that when we charge the plates and we move negative electrons over to one of these plates, it becomes increasingly difficult to do so. The first charge that you add onto there, it's relatively easy to do that. The second charge, it's a little bit harder because the other excess negative charge is already there and is repelling it. The third charge, it's even harder. Fourth charge, it's even harder. And at some point, after so many thousands, millions, billions of charges, it's unable to happen anymore because the amount of energy you would have to change in the system in order to force another charge onto the plate is too high for whatever it is you have doing work on those charges that you are moving around. And furthermore, once you charge the plate, you can think of, I guess, those charges as being somewhat uneasy on the plates. They want to get away from each other, they're like charges, and given the opportunity, they will go back to an arrangement where the system is electrically neutral. Well, here's the opportunity, this connecting rod in the middle. If this is a conducting material, those electrons will flow through that rod, redistribute themselves over the plate that right now is positively charged, and that will result in both plates in the end being electrically neutral. So electric current in many ways can be thought of as the charge analogy to the type of current you're probably much more familiar thinking about, and that is water current, pictured here in the slide. We're familiar, or most of us I would say are familiar with water currents to some degree. Well, electric current is the flow of electric charge from one place to another, just like water current is the flow of water from one place to another. Electric current is defined as the amount of charge that passes through some surface in the amount of time, delta t, and we always use this delta Q symbol for a couple of reasons here. Number one, we're cheating because technically the definition is built on calculus and it's a derivative of a charge function. But if that means nothing to you, ignore that last comment. But you can also think of you're sitting in a system and you're watching the amount of charge that's passed by a given point. So you're actually calculating the change in the total amount of charge that is past that point in defining how much current there is in the system. So symbolically, we can write this as delta Q over delta T, and the symbol that gets used for electric current is I. I'm not sure of the exact reasons for using I, but I do know that C would not be a great choice in this particular context either, since we've already been using C for capacitance and charge. So I is electric current, either capital I or lowercase I, and I think I default to using lowercase I more often. Current has units of amperes. Ampere was, I want to say, French, but again, one of these scientists who a few hundred years ago was working on developing theories of electromagnetism. And 1 ampere is equal to 1 coulomb of charge per second. So if you have 1 coulomb of charge passing your observation point in the system, each second you say there's 1 ampere of current flowing in that circuit. And 1 ampere of current, I guess it's all context dependent, but is a significant amount of current. For example, 1 ampere of current passing through your heart will do some serious damage, perhaps even kill you. Current can be either direct or alternating. Direct just means the current keeps flowing in one direction in the circuit, and alternating current means that it flows first one direction, then the other direction, then back to the first at some regular frequency of switching direction. So we focus in this particular unit on direct current. It's a little bit easier to understand. It's probably less common in your everyday life, though in our battery-powered age, I'm not exactly sure about that statement. The current in your house that you plug in the wall plugs is an alternating current system, and there are very good reasons for that in terms of energy lost in our electrical transmission system. We actually have to get into electromagnetism to make sense of that. In addition, the mathematics of describing an alternating current is trickier. You have to use a cosine or a sine function typically. Direct current is easier to start with and easier to conceptualize. So let's go back to my system of charged plates. So now I've charged my 2 conducting plates. One of them is positively charged, one of them is negatively charged. And then I still use some conducting materials to connect, but instead of connecting just via a conducting rod from one plate to the other, I now connect one of those conducting rods to the side of an electrical light bulb, and I connect the other one to the bottom of an electrical light bulb. And you'll examine in tutorial and lab the structure of a light bulb more closely, but suffice it to say this is going to allow some current to flow through this electric light bulb. Realizing I say that, I gave away part of the question, but what will happen here, and I'll give you a hint, it's not number 1. The answer is number 2, and I guess time frames are relative in here, but first of all, this will light, as I mentioned before. These are the correct contact points to touch this particular type of light bulb in order to force electric current to flow through the filament. If it is a high enough amount of current, the bulb will light, so we have to imagine, I suppose, that it is a high enough amount of current to make that happen. But what's going to happen is as soon as all of these negatives have left the plate on the right and flowed through this conductor, through the bulb filament, through this other conductor, and over to the positive plate, and we've ended up with a neutralized system, then the bulb will no longer light because there's no more charge that's going to be pushed through the filament in that bulb. Okay, a couple more comparison questions for this system. If you have, again, a positively charged plate and a negatively charged plate, and you put a piece of silver in between those two plates, and you put another piece identical in diameter of graphite, which is the same thing as pencil lead, in between those two plates, how do you think the amount of charge that flows through each of those will compare? Will more charge flow through the silver wire, more charge flow through the graphite wire, or about the same amount flow through both wires? Turns out the answer is you would expect to see more charge flow through the silver wire. Silver and graphite are both electrical conductors. You can get them to conduct electricity, and they can be part of working electric circuits. But even among conductors, they have ranges of conductivity, and silver is a better conductor of both heat and electricity than is graphite. So we would expect more of the charges to flow through the path that is easier to make it through, and that is the path made of the silver connector. How about this question? So if I take two conducting materials, they could be silver, they could be graphite, they could be whatever, but wire 1 and wire 2 are now made of identical materials, but you made one that had a small diameter, and you made another one that had a large diameter, and you put those between those conducting plates that were pre-charged. How will that affect the flow of charge through the wires relative to one another? Will more charge flow through wire 1, more through wire 2, or more through wire 3? The correct answer is that more charge will flow through wire 2. It has a larger diameter, therefore it contains more atoms making up its structure, and it has more real estate for the electrons that are on the negatively charged plate to make their way through that material over to the positively charged plate. Here's a place that if you've done any plumbing, this can help you, because if you think about water flow, increasing the diameter of a pipe will actually increase the flow of the water through that. If you decrease the flow through if you decrease the diameter of the pipe, that decreases the flow. Those of you that are heading into health professions, that's a physicist's perspective on buildup in arteries as well. Is the more material that builds up inside your arteries, the more that's restrictive of blood flow, and the less blood can be pushed through that system. Okay, one final question with this system. So I take the same negatively charged plate and the same positively charged plate, and I connect them with some wire 1. They're at some potential difference relative to each other. I take another positive plate that has the same amount of positive charge on it as the one over here, and therefore the same potential difference between the negatively charged plate in the middle and this positively charged plate on the edge, so the same potential difference between the two of them. But the wire connecting these two plates on the right is longer than the wire on the left. How will that affect the flow of charge? Will more charge go through wire 1, more through wire 2, or do you expect the same amount to go through both wires? The correct answer is that more charge will flow through wire 1. It is a shorter path, and so the charge will, well, more than half of the charge will end up flowing through wire 1, and less than half of the charge will end up flowing through wire 2. This is an arena where actually people's intuition is fairly straight on. That can't be said of everywhere in physics, but most people predict you make a fatter wire, more charge is going to flow. If you make a longer wire, less charge is going to flow. And these are both connected to the concept of electrical resistance. So if you increase the length of a wire, you increase its resistance to flow. You make it less conductive, and the flip side of that is you make it more resistive, so less charges will end up flowing through that wire per time. If you increase the cross-sectional area of the wire, That has the opposite effect. You decrease the resistance because now there's more area and more atoms within that wire for the electrons to jump atom to atom and result in a flow through that wire. So we can do, and we're not going to do this in the lab, but if we did, we would find that the resistance is directly proportional to the length and inversely proportional to the cross-sectional area. So we can write resistance, which we're going to use an R to symbolize, is proportional to, and here's L for length and A for the cross-sectional area. So if I increase the length, I increase the resistance. If I increase the cross-sectional area, I decrease the resistance. And as we do so many other places in physics, once we've established the physical parameters that relate to resistance, the way we turn this into a mathematical equality and make the units work out is we introduce a constant. This constant, using the Greek letter rho, is called the resistivity of the material, and different materials have different amounts of resistance and hence different resistivities. If you are curious, Table 19.1 in your textbook gives common resistivities of different materials. Should you have to use some resistivity to solve, say, a homework problem, you could look it up there, or you could look it up via Google. If there were ever a test question involved knowing this, that resistivity would be given to you unless the point of the question was to figure out what the resistivity was. So, back to our scenario here. We've got two charged plates. We have a light bulb that we put in the middle, and we have these conducting wires that connect the charged plates to the 2 points on the bulb, which will allow the electric current to flow through the bulb filament and light. So that's system one. System two, we have a battery that has the same electric potential difference end to end as our two charged plates do, and we connect that battery to an identical bulb, bulb 2. So what's going to happen? Do you expect that both bulbs will light and stay on for about the same time? They'll both light, but eventually go out, and bulb 1 will stay lit longer. They will light and then go out, but bulb 2 will stay lit longer, or bulb 1 lights and then goes out, but bulb 2 stays lit. My answer to this question is either 3 or 4, depending again on how you're thinking about these amounts of time. First of all, we've established that the situation on the left would allow electric charge to flow through the bulb, so that would light the bulb for some period of time. But once we have those plates return to a situation where they are electrically neutral, no more charge is flowing through those wires, so the bulb no longer is lit. Well, it's sort of a similar thing happening in the battery, except in the battery there's an ongoing chemical reaction, and it's not like it's ongoing forever, as you well know, but it goes on for much, much longer than a capacitor can hold charge in a typical situation. And so even though the bulb on the left will go out fairly quickly, the bulb on the right will stay lit for longer. Often, in fact, if this were, say, a flashlight battery and a flashlight bulb, it might be days before the bulb actually goes out. And so if you are thinking, well, I'm observing this in a lab for 10 minutes, then the correct answer would be 4. Bulb 1 lights and then goes out, but bulb 2 stays lit. If you're thinking about, I'm observing both of these systems for a year, they will both go out eventually, but 2 will stay lit longer in this situation. So when we build an electrical circuit, which, by the way, we'll just flip back here, this is an electrical circuit. It involves a source of electrical energy, that is the pump in there, which is converting chemical energy to electrical energy. It has a path for the charge to flow through, and it has some resistance here from the bulb, which is resisting the flow of that charge moving around in the circuit. Well, here's another piece of the circuit. Here's a battery, and post A is, in this particular battery, the positive terminal. Post B is the negative terminal, which means there's a bunch of excess electrons in the region of B, and those excess electrons will flow if this is a circuit that allows it to do so, and we work in tutorial and lab on what is and isn't an allowable circuit. This one diagrammed is, though, and so those electrons will flow through this wire. arrive at one end of something that resists the flow of electric current. Could be a light bulb, but it could be more generically just something we call a resistor, and we'll work in lab with some carbon resistors on your circuit boards. Gets to this point, the electrical charge flows through the resistor. The resistor, of course, resists that flow, and so it flows at a smaller rate than it would if you took this resistor completely out of the circuit. And then it comes back out of the resistor and back to the positive terminal of the battery, where it is again forced over, if you will, to the negative terminal of the battery, and that process keeps repeating until the chemical energy that it was previously stored in the battery has been expended. Well, there's an oddity in electric circuits. Even though we imagine it's the electrons that are flowing from the negative terminal to the battery to the positive terminal of the battery, it's kind of unfortunate the electrons were given the negative a sign attached to them rather than positive, because the way we end up thinking about electric current is that electric current moves opposite to the direction of the flow of charges. In other words, even though electrons themselves move from negative to positive, we're going to define and say that current flows from positive to negative. This is actually better because it's going to mean you make less sign errors when you're doing calculations involving electric circuits. But it is obviously slightly confusing to think about that. Again, if you think about the absence of electrons in an atom, or what is sometimes called electron holes, they will actually move in the opposite direction in a circuit to the direction that the electric charges are moving. However we think about that, the diagram in the middle here is showing how we might draw a diagram of an electric circuit. This is a perfectly legal electric circuit, but most of us are not artists to be able to produce a picture like this and find it easier to draw a diagram more like what we have here in the middle. So this little two lines that are parallel but unequal length symbolize the battery. The longer line symbolizes the positive end of that battery, and so you'll notice the current, symbolized I here with an arrow, flows from the negative end of the battery to the positive end of the battery. Flows around the circuit, encounters the resistor right here, which is symbolized with this zigzag line, and then flows back to the battery. Wires, even though in reality they curve and go in all kinds of directions, are drawn as straight horizontal or vertical lines in most electric circuit diagrams. And what we want to think about is the electric potential, or perhaps the electric potential difference between one point of a circuit and another point of a circuit. So as we process around this loop, what happens to the electric potential? Well, if you go from the negative post of a battery through the battery to the positive post of the battery, that battery has an associated electric potential difference, and when you're moving negative to positive, that means you are increasing an electric potential during that motion. And so as we move from B to A on our circuit, sorry for the hiccup there in the recording. I realized that I'd put the slide where I didn't have my fancy graphics built in the presentation, and I'd hidden the one that had the fancy graphics built, so I paused the recording and went back and fixed that. Again, apologies for the hiccup, but I don't feel like going and re-recording the first 20 minutes or so of this in order to fix that. So let's see, back to this electric potential story. We start at B and we go through the battery to A. That's an increase in electric potential. There it is on the graph. Notice I have no numbers on this particular graph, so if we looked at values of electric potential, simply you would have some value at B. Often it's chosen to be 0. And then it increases up to some higher value at A, and that increase is fairly linear as you process through the battery. If you go from A to C, you go through a conducting wire, and even though everything has some amount of resistance, the resistivities of materials like silver and copper and things that we tend to make wiring from is really low compared to the other things that we tend to make electrical resistors from, such as carbon. And so even though there is some resistance in these wires, the amount of resistance in the wire compared to the amount of resistance in this resistor is ridiculously small, and so we don't, with the devices we have to measure an electric potential difference in the lab, we generally don't measure an electric potential difference as the charge is moving through the wire, because the wire is essentially resistance-less, even though there's a small amount of resistance in it. So going from A to B in an ideal, A to C, excuse me, in an ideal circuit, you maintain the same value of electric potential. Whatever value you arrived at A at will be maintained as you process to C. Going through the resistor then, with the current, the system experiences a drop in electric potential as some of that electrical energy that was being transported by the charges is transferred to the resistor and generally dissipated as heat in this particular system. So the electric potential drops back down. Well, how low? Well, thinking ahead, moving from D to B, I will just be moving through a conducting wire, which we previously said, even though it has a small amount of resistance, we're going to treat it like it has no resistance. And that means there's going to be no electric potential difference from one end of the wire to the other. When I get back here at B, I better be at the same value of electric potential. So I know that D to B is going to be a straight line here, which means going through the resistor, the electric potential drops from some value to some much lower value down here at D. And then D to B is a constant value of electric potential. I get back to B, I'm at the same level, and the process starts all over again. If you think about a real circuit where there is actual resistance in those wires, it does modify the sketch a little bit, and so here I've drawn it in red instead. I still get an increase in electric potential as the charge moves through the battery, but there would be a slight decrease in electric potential as the charge moves through the wire, a much greater decrease in electric potential as the charge moves through the resistor, and then a small drop in electric potential as the charge moves through the conducting wire on the other side. But you would still arrive back at the same value of electric potential if you didn't, flowing around a loop like this. That would be a violation of our energy conservation idea, which says you can't create or destroy energy, including electrical energy. So these concepts of current, which we've introduced and defined in this presentation, and resistance, which we've also defined, are connected to the concept of electric potential difference through something called Ohm's law. Not remembering the particular background of Ohm, though at the time he came up with Ohm's law, he was a high school science teacher, also kind of just working on this stuff on the side. So a battery provides the potential difference for a circuit. Actually, the battery is thought to provide something called the electromotive force, or EMF. And there is a portion of the section of the textbook reading that talks about what EMF is and how EMF is connected to voltage. It's an interesting read. It's useful information, but I will tell you right here that I won't make a huge deal out of it in this particular section of this course. So for our purposes, thinking about circuits, we can just think about the potential difference across the battery, or you can think about the EMF, and we're not going to differentiate between them at this stage. Electric charge flows through the circuit because the battery has provided this electric potential difference. Essentially, in my thinking, I think the battery has forced electrons that used to be spread out throughout the battery over to the negative side of the battery, and that's left an absence of electrons at the positive side of the battery. Those electrons would like to get back to the positive side of the battery. They can't through the battery itself because of the chemical process that's happening inside there. But if you give them a connecting pathway, they will flow through that connecting pathway back to the positive side of the battery. So the charge that flows through the circuit is the electric current, and the electric current, as it's flowing through the circuit, encounters a certain amount of resistance to flow as it's going. So how are these things connected to each other? Well, Ohm's law is the relationship between the three, and Ohm's law says that the amount of electric current is directly proportional to the potential difference. So if you have no potential difference, if your battery is 0 volts, you won't get any current to flow through this circuit. But the more potential difference you introduce into the circuit, the more you'll increase the amount of current that's flowing through the circuit. And this is something we'll see in our experiments that we do in lab and in tutorial. The current is inversely related, however, to the resistance. So if you increase the resistance in the circuit, that's going to decrease the flow of charge. That's going to decrease the electric current. If you prefer shorthand, you'd write Ohm's law replacing current with an I, potential difference with a V or a delta V. Delta V is the most correct, but it's not uncommon to see people shorthand it and just write a V there, and resistance R. Now, this is, in my mind, the best way to write Ohm's law because it's the one that makes the most sense in my head about how these concepts are connected to each other. But I will tell you that most people write it like this way, V equals IR or delta V equals IR. I'm not sure exactly why that is, but it's very analogous in my mind to the way we think about and write Newton's second law. If you think about it, it's the force that you apply to the mass that produces the acceleration. So Newton's second law can be written, and most sensibly is written as acceleration is equal to the net force divided by the mass, but almost everybody remembers F equals ma, not A equals F over m, for whatever reason. I will give a caution here that Ohm's law is not a law in the same realm as Newton's laws of motion are. Well, I suppose now I'm going to provide a counter-argument to that very statement. But Newton's laws of motion, we defined them in Physics 1, and we've used them over and over again in Physics 1, and now even here in Physics 2, because all of these physical situations that we're thinking about seem to obey the tenets laid out in Newton's three laws of motion. In fact, the places where we know Newton's laws of motion seem to not work are on the scale of either the very fast, which is where you go when you study relativistic physics and the theory of relativity, or very small quantum mechanics and the like. But everything else we can get away with using Newton's laws to describe what's happening between the forces applied to an object and the motion of that object. Well, I guess in some way Ohm's law is the same thing. Ohm's law only applies to situations which are ohmic, which is a very circular argument right there. But what that really means is Ohm's law works when the resistance of the object that you are using as the resistor in your circuit is constant or very nearly constant. And some materials, turns out light bulb filaments are among them, change their resistance as they heat up and as different amounts of electric charge flow through them. So a light bulb filament is not something that is considered ohmic, and therefore the light bulb does not strictly follow Ohm's law, even though it follows the general idea that if you increase the potential difference, the current will increase, etc. But the carbon resistors that we use in the lab and that are built into your circuit boards are fairly uniform and constant in their resistance, and so they end up following Ohm's law quite nicely. Ohm's law provides the definition and units for resistance. So the definition would be the potential difference applied divided by the current if you rearrange Ohm's law. And the units of resistance is a volt per amp, but a volt per amp is called an ohm in honor of Ohm, the scientist that proposed this idea in the first place. And we use the capital omega from the Greek alphabet to symbolize 1 ohm of resistance. So we're going to wrap this up by thinking about a ranking task that tries to put these three concepts together. The resistance and the magnitude of the current depend on the path that the current takes. And in the drawing here we see three situations in which the current takes different paths through a piece of material. So I have three identical blocks. Each of these blocks is 4 L0 long, it's L0 high, and it's 2 L0 deep. But in situation 1, I connect it to a battery that has a potential difference of V such that the current has to flow from the 2 L0 by L0 side of this block over to the other side of the block, a length of 4 L0. Take the same battery, but if I connect it to the top and bottom, the charge would flow from the top face to the bottom face. If I connect it to the front and the back, the charge would flow from the back face to the front face, or vice versa. So how do these three materials rank according to resistance with the way they're wired? Well, resistance, again, recall, is directly proportional to the length of the wire, and inversely proportional to the cross-sectional area of this. So the one that's going to have the highest resistance will have the smallest cross-sectional area and the greatest length, and that's situation A here, where the length it has to travel through is 4L naught, and it has a 2L naught by L naught face of the block for the charge to flow through. The one that is least resistive is the one here in the middle, B, because the charge is flowing into the side that is 4L naught by 2L naught, and it only has to travel a distance of L naught. And situation C is right in the middle in terms of ranking the resistances. If we rank them according to current, Ohm's law tells us the answer almost immediately. Ohm's law, you'll recall, says current is equal to the potential difference applied across 2 points to the resistance of the material in between those 2 points. The potential difference in each of these situations is the same, hence the VVV labeling on the battery symbol, but the resistance is not the same, which we've just established. So the current is going to be inversely proportional to the resistance. In other words, the one that has the most resistance has the least current, and the one that has the least resistance has the most current. Therefore, we expect the current to be greatest in situation B and the smallest in situation A. It's the exact reverse of the ranking for the resistance part of the question. This concludes the online lecture for current and resistance for General Physics 2. Hopefully this was a helpful resource for those of you that are working on learning physics. And again, if you've noticed any errors in the presentation, I appreciate your notification of that. Thanks.